our beloved lecture. My name is AHMAD Harith AMRIN. My matrix number is 23 13 11 83 with alongside with my group partner Muhammad AKMAL 23 13 11 200. And today we are presenting our CAE lab project on design improvement and analysis of a car tow hook. Today we will discuss the finite element analysis and thermal structure of the design that we propose. Go through on introduction. Car tow hook is a critical structural component used to pull or rescue vehicles when they are stuck or broken down. A car tow hook is a critical safety component subjected to intense mechanical stress. The problem that we are trying to overcome is extreme stress concentration, environment aggressors, and material inefficiency. The first problem is we are going to talk about the towing operation generate significant tensile force that build up at connection points, threatening sudden bending or catastrophic failure. The next is environmental aggression. So the real world tow bars operates under high harsh ambient thermal conditions and localized engine/exhaust pipe heat. And the third is material inefficiency. So heavy non-optimized structural steel assemblies increases vehicle dead weight, decreasing overall fuel efficiency and manufacturing economy. Our primary objective is to investigate how operational thermal load affect the structural integrity of this assembly. We aim to track the maximum equivalent von Mises stress, structure deformation, and localized factors of safety across multiple testing parameters, especially specifically looking at variations in uh, beam thickness, operational temperature, and material profile. Scope and boundaries. Um, so this is the boundaries and the scope that we are going to be used in our analysis, which is 5-part CATIA CAT assembly, which 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 has the crush bar itself, the bracket adapter, the hook loop, and the bolt fasteners. We also focusing on static multiphysics, which is structural mechanics, thermal expansion, and topology solvers. The third one is mesh controlling compliance. By doing so, we limiting total nodes strictly below the student licensing ceiling of 178,000 nodes. The other boundaries that we are not going to talk about is dynamic crash event, which is a high-speed crash dynamic and dynamic shock impacts. The second one is physical prototyping. This is the thing that we are studied that relies strictly on virtual FEA simulation with zero experimental testing. And third one is manufacturing physics. Metal casing shrinkage, shrinkages and metal forming cost metrics are ignored. Essentially, we are doing analysis purely on theories, and we are not going to apply all of our theories to the real world. Method. This is the flowchart of our analysis. So we started with CAD modeling in CATIA. and then after that we export it using steps STP, and we export it into ANSYS for our analysis, and then we assign material and contact, and then we generate mesh and also set our boundaries condition. After that we start with our design analysis, and after that we identify the critical part that is prone to failure, and after that we do the design improvement, which uh, which is um, increase the thickness and redesign the the internal structure, and then after that we select the best improvement after, and then we do three analysis, which is different material analysis, thermal analysis, and topology optimization. And after all of that, we compare all of the results. Geo Geometrical model construction. Our methods begin with a parametric CAD modeling ICATIA. We built three distinct assembly models that evaluate effects on geometry scale. So we started with doing the beam itself, which is part 4, and then we made the assembly for the toe hook, which consists of the toe ring, the toe hook, and the toe lock nut. And after that, for the final part, we designed the bolt assemblies, the bolt fasteners, so it will be part of the design. Towing load justification. We justify our structural mechanical force via standard rolling resistance physics. Our formula that we have decided to use is tow force is equal to mass times gravity times the coefficient of rolling resistance times the transient peak acceleration spike. So the coefficient of rolling resistance is where we accounted for the frictional that are created on the asphalt on the road, and the dynamic safety factor multiplier accounted for the extra force needed to pull the car from the gravel or from a surface that is not tarmac onto a flatbed. So our mass for our vehicle is 3,500 kilogram, and we decided to go with 0.018 for our coefficient and multiplier of 2, and then we will get 1,236.06 Newton, which equates to 1,000 which roughly equates to 1,250 Newton. So with this force that we calculated, we can simulate the horizontal force that will be applied to our analysis. Material properties assignment. So we have added three types of the material, which is high tensile structural steel, SPFC 590, high strength steel, and 6082 T6 aluminum. The aluminum is added because we need to run our material variant analysis, and we decided to add another properties, which is ultimate tensile strength. It will simulate real life scenarios because it is a properties where the metal has a sustainable stress that it can handle before it physically tears apart or fractures.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AKMAL bin Muhammad JOHAN. And so now let's moving on to mesh generation and verification. We chose tetrahedron elements with a global 6 mm sizing to accurately capture complex curve and fillets to the crash bar assembly. As you can see in the table, our mesh remains consistent between the original design and modification 1. However, adding internal grips for modification 2 naturally increased our total node count to just over 93,000. Crucially, this maximum node count remains well below the ANSI student license limit of 178,000, ensuring our model runs smoothly without any software constraint. Next, let's look at contact modeling and boundary condition. For this setup, we configured bonded contact at the bracket to bumper interface and around the securing fasteners. As shown in the ANSYS interface here, this approach simulates a welded connection, effectively forcing the components to behave as a single rigid body under load. This ensures realistic load transfer across the assembly during our structural simulation. In addition to bonded contacts, we implemented frictional contacts at the hook to housing slide interface. By applying a friction coefficient of 0.15 as shown in the properties table, we allow for realistic force translation while preventing any unphysical mesh overlap. This specific contact definition is crucial because it allows us to accurately capture the peak shear strains where the components interact under load. Next, we establish the boundary condition by applying fit support to the simulation model. As highlighted in the blue on the graphic, we constrain all translational degrees of freedom, setting X, Y, and Z to 0 degree. This replicates how the bracket secures rigidly to the vehicle's chassis frame. This crucial constraint keeps the entire assembly grounded, allowing us to capture realistic deformation when the load is applied. This brings us to the results and discussion section of our analysis. Over the next few slides, we will take a comprehensive look at our simulation findings. Specifically, we will review the overall stress distribution, safety factors, and the distinct impacts of our material swaps and thermal variables. We will also look at how our topology modification hold up against core engineering principles. Now, let's dive into the structural result. As you can see, improvement number 2, featuring the internal stiffening grips, yields the most optional performance. By adding these internal grips, we successfully distribute the loads much more effectively. This dropped our peak stress significantly down to 73.5 megapascal, which is 33.5% reduction compared to our original baseline. Consequently, this optimization significantly maximizes our factor of safety, bringing it up to a highly secure of 5.3527. Finally, we evaluate lightweighting performance by comparing steel against aluminum using our optimal layout. Switching to aluminum reduced the overall assembly weight by roughly 65%. However, it introduced a clear structural trade-off because aluminum has a lower Young modulus. It acts like a stiff spring. This flexibility successfully reduced peak localized stress to 73.5 megapascals, but it results in 3 times higher total displacement compared to steel. Ultimately, this trade-off maximizes our factor of safety to an impressive 6.6656. Next, we analyze how temperature changes impact the assembly. Because of our fixed boundary condition, physical thermal expansion directly translates into localized compressive stress. Following the formula shown here, theta equal to E times alpha times temperature. Looking at the results, normal good condition at 60 degrees already more than double our peak stress. If we factor in exhaust heat raising the temperature to 80 degrees Celsius, peak stress spikes to over 373 megapascals. This dramatically drops our factor of safety to just 1.12, highlighting a critical area where thermal management is absolutely necessary.
This is the result. We decided to go for 75% mass retention, which is a 25% weight reduction. Based on our topology analysis, on ANSYS, we got the part where it was hollowed out on the back side, and the part that is less hollowed is where the tow hook connects to the crash beam. So we need to redesign it and in CATIA and rerun our structural static analysis. And by doing so, we got a 77 megapascal of peak stress, which is a lot less stress than that we got from our original structures. Uh, what when it comes to deformation, we got slightly more deformed because of the materials that we already removed. So the structure will be less what do we call less strong. But because of our deformation is from 0.107 to 0.184, it is very minimal. But our factor of safety was increased slightly from 5.35 to 5.40, which is a success for us because of we remove some of the material, the stress redistribute itself, and because of that, our peak stress drop and our factor of safety increases.
To explain the underlying physics, let's look at the engineering phenomena of stress concentration. Naturally, structural force crowd around sudden geometric shift. By implementing smooth radius fillets and diagonal ribs in improvement number 2, we successfully spread out these structural force lines. As the chart shows, this physical optimization lowers maximum stress by 33.5%, controls a deformation, and drives our factor of safety up to its highest value of 5.35. Next, let's look at the physics driving our material selection. When we compare steel to aluminum alloy, we see a highly favorable shift in performance because aluminum distributes the loading environment more compliantly. It drops our maximum stress down to 73.5 megapascals, though it does increase total deformation. Most importantly, look at the factor of safety chart on the right. Our safety margin jumps by over 24%, climbing from 5.35 to an impressive 6.6656. Lastly, let's look at the physics of thermal expansion. Because our mounting brackets are completely locked in place, the material is physically prevented from expanding as temperature rises. Blocking this growth pull up massive compressive stress within the structure. As the chart highlight, when moving from baseline up to 80 degrees Celsius, maximum stress skyrocket to 373 megapascals and deformation spikes. This severely narrows our safety margin plunging our factor of safety down to a critical 1.12.
So design improvement based on the based on our observation when we run the analysis, we get 77 megapascal, and while the original still have 91.5 megapascal, which is 20 megapascal less than the original, which is a great success. Also, our deformation does slightly increase because of the material that we remove. So the structurally it is became less weaker, but it is minimal. And the thing that we are going to look at is factor of safety. It is increased by 0.1, which is a great success for us because we successfully reduce the material on our design while maintaining a better factor of safety for the crash beam. And this translates to 15% lower stress on our crash beam. In conclusion, um, so the conclusions are that we found two types of findings, which is quality findings and quantitative findings. The first one is fillet dinner stiffness ribs. Remove sharp corners when forced bottle up, preventing failure. Switching the crash bar to aluminum increases elasticity, letting it flex to distribute loads. And the third one is topology solvers successfully identify structural dead zone, enabling lighter design. As we can see before, um, we dropped from 90 megapascal to 70 megapascal, which is a huge gap. So the quantitative finding that we have found is that rig modification number 2, the design dropped 35% of drop stress by 35% and increased the safety factor to 5.35, while the aluminum alloy that we changed to lowered the peak stress to 3.751 megapascal, achieving a 75% weight saving. And the third one is thermal exhaust heat. It is the the stress was spiked to 373.83 megapascal, and because of that, the factor of safety dropped to 1.12, which is okay because it is still above 1, but it is not, in my opinion, it's not good enough. So that is all from us. Thank you and have a good day.